Okay, so at this point we know that the definition of a strong acid or a strong base is that it will completely dissociate or break apart into its constituent ions. And that makes it pretty easy to infer what the pH or pOH of a solution is, because you just assume whatever the initial concentration of that acid or base was, that's going to be the final concentration at equilibrium of the hydronium or the hydroxide ion. But with weak acids and bases, it's quite a bit different. And so it's not simply the same as saying it's like a dilute strong acid. For instance, a weak acid is not the same as saying like 0.0001 molar nitric acid, because nitric acid is still a strong acid, it's just really dilute. And we know that for strong acids, K is very, very large. But a weak acid or a weak base, really what that means is the equilibrium means the much smaller equilibrium constant. So how do we think about solving these things? Well, generically, if we think about HA as our weak acid and we just dissolve it or react it with water, it's going to dissociate and it's going to make H3O plus and A minus just like we're familiar with. But the word weak means that K is small. The other way to think about that is the dissociation then is less than 100%, right? Because if you have a small K, that means, right, K is products over reactants. It just means that you probably have more reactants than you do products at equilibrium. That's what that means. So how do we move forward in conceptualizing it? The other important takeaway here is that K, and really when we're talking about K, for acid dissociation like this, we mean Ka. That's the specific flavor of any reaction like this, strong or weak. The equilibrium position of this is its acid dissociation constant, or K sub A. The size or the magnitude of K tells us what the strength is. So before we had this table that showed us the relative strengths, that table was just ranking them based on their Ka. Means that the larger Ka, the stronger the acid. And that should make some sense based on the definition of what K is, right? K is just products over reactants. And so for this generic acid dissociation reactant, that's going to be H3O plus times A minus over HA. We don't include water because it's a pure substance. So when K is large, it means the numerator has to be large. The denominator is really small, which just means that the reaction lies heavily towards the right, or in other words, it's 100%. And for small k's, it means that there is more of the HA in solution at equilibrium, which means a smaller K. And so a table would look something like this. I'm just tossing on a few here. But if we have strength as our y-axis increasing as we move towards the top of the axis, and we have a few acids, HCl, HF, and ascorbic acid. Ascorbic is the same as vitamin C, and their corresponding Kas. We can see HCl, which we know is a strong acid, has a Ka of 2 times 10 to the 6th, which really simply means, if we think about this equation, it simply means 10 to the 6th. There's about 10 to the 6th times more numerator than there is denominator. 10 to the 6 is a million, so it means that at equilibrium there's a million times more product than there is reactant. That's what it means to be 100% dissociated. But if we look at HF, it turns out HF is actually a weak acid because look at his Ka. It's 10 to the minus 4. So you go from 10 to the 6, positive 6, to 10 to the minus 4, that's 10 orders of magnitude. That's a huge difference in strength, which means that at equilibrium, what do we have? Well, at equilibrium, we have more HF than we do anything else because it doesn't want to dissociate. And the same is true for ascorbic acid, it's even weaker than HF. Because the scale is exponential, just like pH, we can do negative log of Ka, and that gives us this other relationship. So pKa is equal to negative log Ka. Nothing fancy there. We already knew that P is just negative log of something. And that just simplifies this so that we can talk about the pKa's of these things in whole number values and quickly make assertions about what's stronger or weaker. So in this case, the smaller the pKa, the more strong it is. And in this case, if you did negative log of 2 times 10 to the minus, or 2 to the positive 6, you'd end up with a negative number. And so the pKa for strong acids are often negative, and for weaker acids, they're positive and large. And that just is a quick reference for the strength of acids.